Good morning, good afternoon, and a very good evening to folks who are joining us from different part of the world. Thank you for joining us today. I am Aditya Sharma from E2E Cloud's marketing team. E2E Cloud is an Indian-based accelerated cloud computing platform for all your computing needs. And we sure hope that you will enjoy this session and learn a lot from it. Today with us, we have Mr. Srini Chilukuri, who is a serial entrepreneur, founder, and CEO of TensorGo Technologies Private Limited. Srini was also the founder and MD of FlexEye and HyperCat, which built the first IoT standards recognized by BSI. He was the producer of some top best-selling games in the world, such as Mortal Kombat and Dance Central. Expert in deep learning and custom neural network, and is a turnaround specialist. With us today, we also have Sri Sai Akhilesh, sir, who is a lead computer vision at TensorGo Technologies. He specializes in building state-of-the-art computer vision applications using neural networks and transfer learning. He has experience with various APIs such as TensorFlow, PyTorch. Akhilesh sir has also worked with clustering and ensemble techniques like bagging, boosting, using algorithms such as random forest, GBM, XGBM, and CatBoost. Lastly, but not the least, meet Aniket Shrivastav, sir, who is a senior computer vision engineer at TensorGo Technologies with a strong background in computer science. He has extensive experience in the health, wellness, and fitness industry, and is skilled professional in computer vision and machine learning. Aniket sir holds a Bachelor of Technology degree in computer science. With that, let's move over to Srini sir and begin the session.
Thank you, Aditya. Thank you for the introduction. And it's good to I can see everybody here. And first of all, thank you E2E for arranging the session. I think hopefully it's will be pretty much can useful for everybody too. So let me quickly share the screen. Okay. Sorry, I'm just having a little bad throat. So let's get started. So what is TensorGo, right? So we're a low-code platform as a service company that's building the deep learning solutions for various other enterprises, whether the enterprise organizations from the automobile industry, is from the sports and entertainment, BFSI, education, governments, or any of them, right? So we allow these complex algorithms to be deployed on our platform and expose them as an API. Somebody can really mix and match and build whatever they wanted up just by integrating with few lines of code with APIs. So we are a Gartner Cool listed company as well. And we are also the winners of the Oracle worldwide events too. So before I go into details, I'd like to show you a video where you can really understand the kind of a work that we are really doing, coming more towards the deep learning side. So if you see in this video, you see a lady who is actually drawing the vehicle. She's feeling drowsiness, and you can see that the person is feeling drowsiness, which has been highlighted here. Not only that, there's a distraction that's been highlighted at here as well too. We also capture the emotions, the head pose, the heart rate, the ethnicity as well, the demographic profile, and everything else. The heart rate is something that we capture just from the camera itself too. But if you see here, she picked up the mobile phone. Even the mobile phone is highlighted it here. There's a distraction that's been monitored as well too. So what is the worst thing that could happen that somebody is losing a life on the road and you don't get a message about it, right? So now this can actually provide a lot of information. Now, if you really see this, the person at here can holding an oximeter, which is showing us as an 82 here, and the reading that for API we're showing us that's an 83 here. So now it shows like it's an Indian, 25 to 30 years old, and he does a little bit of workout. He comes back and sit here, and then you see that the heart rate is bumped up to 102 here, and it's about 103. So these are kind of a very the unique things that we actually developed. And this is another one which actually can identify if a person is deceptive or not, which means like how the person is, how truthful the person is. For example, if I really see the Mark Zuckerberg hat here, this is a code trial that happened some time ago, and we actually took that video and processed our algorithm on top of it, and then we see that he's pretty much truthful here.
I think the categories of I'm not sure I can give one, but can I give a bunch? So there are three categories that I was questioning why I
And
was.
there's another video where a professor was involved in terms of saving his students who consume the drugs during a code trial. And he was actually, the code trial video was been published very long ago. And after that, for 2 years of something else, he released a blog saying that his intention was only to save the students who consume the drugs. And he's trying to, withhold some of the information. And when we actually took the 2 years of old video and we processed it, it shows like it's pretty much deceptive here. And our algorithm can work at almost about 83% of accuracy and higher. So we tested this, and some of the customers use in their investigation process as well too, where it can work only with the camera and the tonality part of it, without having any kind of a sensors attached to it. And this is more about a physical test, a paper-based test is happening out. Somebody is gesturing, you get to know that the people are gesturing it. People are looking at the size, you get to know about it. Not only that, we can even actually understand the extent of the paper as well too. Now this goes beyond about it. We can understand the potholes, which is everywhere does it, but we can actually map that onto the maps and then compare that together and then do that too. And this is more about a virtual parameter overlay, where we can understand where the brands are and how many impressions it's happening out to be. And we go an extra level in terms of doing the virtual parameter overlay, which means like now previously Adidas was there, we changed that to Coca-Cola here. For example, now you see here, this is a match that's happening out. And you see the Nike ad was actually not there in the ad, but we were able to place the Nike inside the ad during the runtime itself. So this is more about something called as a virtual parameter overlay is something we do that. Now this goes beyond in terms of identifying the food and also the calories in the food, who's taking what, and all of these things up as well too. So now let me go through a remaining part of it where you see here, this is basically, we're able to take a satellite image, which is a very bad quality, where you find a very off-narrow kind of an image, where you see the skyscrapers actually covering to the part of the roads, buildings as well. And we took those kind of images and we are able to process with our algorithms to identify where the roads and the buildings are. For example, if you see this kind of scenario here, you will not be able to see even the roads here, which are being covered by the buildings or with the shadows or with the trees that here. So this is something which is a very, very different as compared to any image that you can actually get from the drone, but we're still here, we're able to identify where the roads are as well too. So these are kind of a very different kind of an APIs that we build it, which can be, you can mix and match and you can build an application, whatever you want it. So now in this scenario, what happens is that anything that you want to do at a deep learning at an enterprise grade level, the frameworks, the existing frameworks that we have it, any of the frameworks are not really ready that you can actually build at an enterprise grade level because of the complexity that's involved in it. And they are very time consuming and expensive as well too, because all of this needs to work on a GPUs. You need to have a great partner like EDU or someone else that you can work along with it to see that your processing costs and the rates are kind of much lower so that you can actually provide this to your customer where they can really consume it at a lower cost, because these are going to be very expensive solutions. And if you see that there's multiple situations where the people, the infra and data assets are pretty expensive, the people that works on this, can more of a company with engineers, data engineers, data scientists, it can be very expensive resources. Infra, it all works on the GPUs, so it's going to be expensive too. And the data sets, you don't get the data sets so easily because, for example, if you talk about the medical data set or any kind of proprietary data set, you need to have some kind of a joint venture with them, a kind of collaboration, so that you can actually can have an access to the data set and then build on top of it. It takes months and years to build anything else, a very, very long time to build it. And if you really want to get it to production and you want to do a testing of it, you don't have any kind of a very defined way, like in how do you test these algorithms either. And especially when you talk about the custom algorithms, for example, when a customer came to us and it says, hey, would you guys be able to identify if a person is lying or not just from the camera? We cannot afford to have the sensors there or any kind of a polygraph test or anything. We cannot do it because of so much of complexity. Could you help us doing it? So that's a kind of very custom neural network that we need to build it. And it requires a lot of effort to do it. And it has a very different approach for it. So when you want to do these kind of things, the complexities is a way that you actually go beyond what any customer requires it. So you require a kind of a system that can really manage and have a kind of a high performing computing systems, which where they are generating higher volumes and velocity of the data. And you need to have another system that's actually taking these volumes and velocity of the data, doing the data turning, doing the complete data engineering, and pushing back that into presentation layers so that seamlessly you'll be able to work with it. So we're talking about one system that's actually generating a higher volumes of the data at a higher velocities. And then you have another system that's actually working in parallel with it, doing the processing and pushing to that side, which we are talking about a computer vision deep learning algorithms to one side, engines to the other side, and there's a big data kind of engine that's working to the other side. So this is what is which is really required. So that's where the TensorGo comes into picture. What we do is that we allow all of these things to happening in our system. I'll show you very quickly a product that we actually built on top of our platform, which is called as an ML+. So there's a little science that I would like to give you before we go to the product part of it. This is the brain that we actually see it. This is called as a hypothalamus, which is responsible for any kind of a impressions that a person would carry it. Whether it's and it also affects the heart rate, the various of the physiological parameters like respiration rate, your BP, or any other brass in it. Motor cortex is the one that we actually try to override it. So now the facial nerve is the one which is connected from the hypothalamus, comes onto the face that actually, it actually branches us into tiny nerves. These tiny nerves provides the micro expressions. So there's a various science where 15-20 years of research has been done in one of the top universities. We collaborated with them. And then we worked in terms of the research part of it, where we took the licensing of that and built some kind of a technology on top of it, where it can really identify the human emotions, various the physiological parameters like heart rate, respiration rate, BP, and various of the parameters as well too. So now we implemented that and then made that as an APIs. So now let me quickly show you a product of ours. This we call as an ML+. What happens is that you can really see here. So these, so we can actually directly take a video directly from a Zoom call, something like this, a WebEx from a Teams, or even if the data that's been stored in some kind of a an offline storage like an S3 bucket or the S3 Azure storage or object storage from Oracle or whatever it is, we can store the video there. All we're going to give is like a meeting ID. Once you give the meeting ID, we pull the the particular meetings. It provides all the details of the meetings. It also provides like who are the people participants in the meeting as well automatically. Now, I would like to select this meeting, and we select who the subject is. For example, now I have to say like the subject is Amelia. Then I go here, choose Amelia as a subject, and then what it does is means like it basically monitors Amelia. What are the results of insights I would like to take with Amelia here. So now, so that. So now if you really see that, now the subject selected is Amelia here. You can see the red dot here. And now I'm playing a video, which we are directly taking it from the Zoom. So it's playing for the Zoom. Now it actually automatically identifies who are the participants here. It gives a percentage of participation. It says like an Ellison and Amelia are here. And you get to know like who is contributing to what percentage or a call. And you also get to know the emotions of the person as well, how they're feeling about it. For example, if I really see that Amelia here, and so now she'll come here. So that's Amelia. So now it shows her approximate age and city, and it shows her emotions as well, how the emotions are looking like to be, how neutrally she is, and with surprise she looks to be. So you get to know about it. So now we also get to know the heart rate as well. I get to know the heart rate variation. I get to know the stress levels, the respiration rate, and the truthfulness of a person as well. Where the person is truthful and where the person is not truthful is also something we get to know about it. And again, our algorithm is improved, is actually in the production with some of the customers as well using it. It actually provides more than 83% of accuracy as well. Now, while we're doing all of those things, it also does the diarization. While doing the diarization, it also knows the transcription. It does a transcription as well of the person. Not only that, it also provides the meeting notes of the meeting. It also provides an action items for the meeting as well too. Now, it could even know the voice biometrics as well. You get to know if the same person has actually joined the call or not. You want to know about it, you can know about it. And the face biometrics is also something that you can know about it. So now it here, the face is there. You get to know voice biometric, face biometric is all matched. It's pretty much truthful. Our lip sync is there. I also go to know like where the person is actually looking on the screen and where the eye gaze is there. I get to know the head pose, the heart rate, blood oxygen levels, respiration rate. The blood pressure is something that we're still working on it in terms of deploying into the production level. It's still in the beta phases. And again, the call summary is something I get to know the complete call summary as well, and how the person is with the emotions, the stress levels, and the truthfulness to a lot of them. We also get to know the eye gaze at a various delta period of time, how the person is working out to be. Now, we also introduced this lip sync very recently. Why? Because you see some of the people that attending the interviews, who are in front of the camera just doing the lip sync, but there's somebody behind the camera who's actually doing the voiceover. And this can actually be identified very easily as well too. So now, how is this useful, right? A medical institution is actually using more in terms of enabling the features like in heart rate, blood oxygen levels, respiration, and also the emotion, the stress levels of the person as well too. There's a recruitment company is using in terms of the identifying the emotions, the stress levels of the person, the transcription, meeting notes, a lip sync, and then action items too. And there's a sales company that is using in terms of providing the training and the sales monitoring to their employees, to identify how they are over a call, how the contribution is happening out, where having the meeting notes and the discussion items, the action items as well, and also knowing about whether the customer is intended to buy the product, the conversations is leading to appropriately or not. Just to let you know, we don't use any of the chat GPT. Everything has been built by us in-house. Of all of these algorithms too. So now let's get back to the this piece, and how do we do this, right? Now, it's as easy as that. All of these are actually built and deployed on our platform. And what this huge platform does is that it optimizes the tensors, the way we use it, the hardware that we use it, and actually expose it as an APIs. Now you have a bundle of APIs. All you got to do is that you don't need to have any kind of a deep learning logic, nothing else. All you got to do is that you just need to mix and match the APIs and build whatever you want it. The way it looks like is that you have a highly scalable, secure infra, and then the green portion is the PaaS, which is a platform as a service, where you have a computer vision layers that are working with it, integrated tightly with the data layers, the big data layers. And we have a lot of AI and business logic layers that's underlying there. And these are, again, back exposed as a microservices, back as a SaaS. So if there is as a legacy application that is already there, you want to integrate them, one of the features of it, then all you got to do is that just integrate with the 10, 15 lines of code. And all it requires is a video stream. We save a zero amount of the data on our servers. And all it provides is metadata, and that you can structurize and build it what you want it. And the customers can actually integrate that back into the front-end layers, do the analytics back into it, and the data sources is the we want. This is how the very high level our platform architecture looks like it. And we provide more of a SaaS licensing and also the PaaS licensing as well. PaaS is provided only to the customers who has a higher requirement of churning the data, and also they have budgets with it. But otherwise, SaaS is something that's been provided to it. So I would like to stop here so that the rest of my team can continue with it. So I would like to welcome Akhilesh. He can go a little more technical into details, talking about the tensors and how we are using it, how we are optimizing our models and ensuring that they can really provide the really fruitfulness for the end customer too. You, Akhilesh. Thank you.
Thank you, Srini. Thank you very much. Let me share my screen. Awesome. Good afternoon, everybody. I am Akhilesh. I'll be speaking a little bit into technicality, and I would speak specifically in terms of how we leverage Tensor Cores and NVIDIA GPU specifically for our use cases and in generally as well. So I would just speak a little bit about what exactly Tensor Cores are about. I think TensorGo is usually is a performance booster for any kind of GPUs that acts in terms of processing any convolutions, any matrix multiplications. So just to put it in an analogy, just imagine a GPU as a classroom and let's imagine that there are all the CUDA cores as PhD grads in the classroom, and then each one has their own wider domain of knowledge, and there are few tensor cores available in the same classroom as well. And the tensor cores jobs are just to analyze what mathematical operations they are supposed to do, primarily to matrix multiplication and matrix addition. So if I give a question paper to this classroom called GPU, and the context of the question paper would be in terms of training an AI algorithm. So then all the CUDA cores would have completed this in 3 hours, but whereas in Tensor cores, they would have completed within just 1 hour, because all the AI algorithm require is to process matrix operations, mostly multiplication and addition. And TensorGo especially are specialized into this application, and they don't have to worry about any kind of memory management and any kind of other GPU core GPU core operations. Tensor cores is only sole purpose is to compute mathematics, nothing else, no memory management. And it is simply denoted by D is equal to A into B plus C, where A, B, and C are tensors of 4 cross 4 dimensions, which we can call it as mixed precision, where you can multiply two mixed precision, that means two floating point of 16 operations, and then add up that to a floating point 32. The reason why tensor core does a floating point 16 is because to accelerate few things in deep learning layers. So, I mean, as just we were speaking, acceleration, the time reduction in terms of inferencing and as well as the training. It opens the doors to a lot of other possibilities as well. Uh, just jumping to the next line. So, just a quick wonder around what exactly are CUDA cores and what exactly are tensor cores. I wouldn't call it a significant difference, but all the tensor cores are present inside CUDA cores itself. Tensor cores are basically a few set of specific operations present inside CUDA cores. The job of CUDA cores usually lie in terms of handling local memory, global memory, handling GPU capacity, as well as processing, I mean, using CUDA cores as well. Tensor Core's job is only to worry about handling matrices and in terms of half precision, which is nothing but floating point 16. But and which helps again, tensor cores again are for meant for parallel processing and speeding up deep learning and AI workloads, deep learning or ML workloads. If you just think if you take a few key evident differences between CUDA cores and tensor cores are nothing but CUDA cores basically are available for a wider aspect where they can handle heavy multimedia loads, probably that might be gaming, that might be heavy duty video processing. Or if you just think about tensor cores, then I would probably say that tensor cores process a lot of machine learning and deep learning tasks itself. And if you just think about the speed up and the calculations, how they do is that, just to put in simple perspective, CUDA core probably it would do 1 into 1, probably in a one GPU cycle, and whereas in tensor core it would be able to do literally a matrix multiplication, 3 cross 3 or 4 cross 4 matrix multiplication in just one GPU cycle. All adding up all this optimizations which tensor cores can do in terms of AI and deep learning, the CUDA and cuDNN and the GEM packages provided by NVIDIA, which can vividly be accessed by all our deep learning frameworks, TensorFlow, PyTorch, where it gives a very good accessibility to our tensor cores directly. On the graph, if you see on the right side, this is a very raw comparison between without Tensor Cores GPU and with Tensor Cores GPU, P100 versus a V100. I think we can easily observe that in terms of performance, there is a 4 to 10 fold improvement in terms of performance if you consider tensor cores for AI. And if you keep on increasing the cores exponentially, the performance also increases exponentially. There are few things and few benefits which we have in terms of tensor cores. The two key parts for every data scientist or a computer vision engineer, or probably even a data engineer, I would say acceleration and efficiency is two most important parts for processing for creating your deep learning or AI pipelines. So here, in terms of, again, if you talk in CUDA cores accelerates everything given, but Tensor Core accelerates it even more to the next level. So for example, if I'm a researcher and I'm researching, I mean, that's probably a job for everybody here. All the data scientists, all the computer vision engineers, whoever are there, they are supposed to experiment a lot of algorithms with a lot of hyperparameters, a lot of test cases, a lot of different data sets. So all this take a lot of time. Probably let's imagine that without tensor cores, you're trying to process different kinds of algorithms, hyperparameters, and data sets. It would probably, let's say that it would take around maybe 4 to 5 days to process for a certain use case. Whereas if you in the same place, if you leverage tensor cores, that would reduce your time from probably 3 to 4 days to a day or a day and a half at maximum. Because if you leverage tensor cores with half precision, that means floating point 16 operations, that would scale your specific layers of convolution and batch normalization and whatever your optimizer is. It would increase your booster performance 6 to 8x, 8 times the performance. So in the same context, you could reduce the training time, as well as you can increase your throughput of your model. And if you talk about efficiency, I think if all the modern GPUs, I mean, recently, whatever GPUs that NVIDIA is trying to launch or they have already launched, I think Tensor Core has become one of the core parts of it. Because I mean, NVIDIA is called an AI company now, I guess, because they handle a lot of AI processing units, and their GPUs are also well established in terms of handling matrix multiplication, and specifically in terms of tensor cores. So, I mean, as the graph you can see below is basically how a operation tensor core uses. It gets a matrix and it divides the matrix. It compresses the matrix into floating point 16, and then probably, I mean, again, this operation only happens for a few specific layer like convolution or batch normalization, or when you're trying to forward your neural network. So it would further I mean, it would compress your mathematical operation, and then it would feed forward your whatever operation that it did, probably a multiplication operation here, and then it would convert that to a floating point 32, which is a full precision. So what am I trying to into floating point 16, accelerate this tensor probably into 6 to 8 times of the speed, and then merge that into floating point 32, such that to not lose any kind of in terms of efficiency, in terms of accuracy of the model, to maintain the full precision again. So just moving ahead here. So there are a few advantages and disadvantages of tensor cores. The primarily advantages, what I would say is that it would reduce mathematical computations. I mean, if I would say 1 into 1, I would say it is 1. But when you ask me what is 500,000 into 120,000, that would be very tough for me. In the same context, if you take the same context to a tensor core, it would be able to do what is 640 into 1020 as well in fraction of seconds, because it has the capacity to do local computation. That means it breaks up the big tensor into small tensors, process it pretty fast, and give the result back. So in this context, this is where the computation of the processing computation of the cores will reduce, and the memory allocation also is optimized if you start using leveraging tensor cores. For example, if you start off with a model and if you start creating training or inferencing, then at the point of inference or at the point of training, if a model occupies around 4 GB of memory without tensor cores, then if you start leveraging tensor cores here, if they are available in that GPU or supported in that GPU, then the same memory allocation would be reduced furthermore to 2 GB or to 2.5 GB. And the most important part is that it eases the burden for memory bandwidth. That means say from position A, moving a tensor from position A to position B. That means moving from one operation to another. This tensor accelerates the operation such that it moves faster in the algorithm itself. Let's say you have a weight of floating point 16 and it does a forward pass, and of course there is a loss of floating point 32 because the model is in floating point 32, and then you cast it to FP16 back again, which is nothing but a small overhead here. And again you do a back propagation with floating point 16, which accelerates your algorithm in a very better way. I mean, what am I trying to emphasize here is that the key parts of algorithm operations are accelerated using tensor cores. There are few small overheads of simple casting. That is that means that getting floating point 16 to floating point 32, but this can be given out because I think the significant part would be to accelerate the operations here, forward pass or back propagation algorithm present in your neural network. There are many few disadvantages using tensor cores as well. The most important would be vanishing gradient. I think this problem still persists. I mean, either you go with CPU or whatever you go, the vanishing gradient problem will be there. But if you start leveraging with tensor cores because of the mixed precision that you're trying to do, it might be little higher comparatively to the training with just CUDA cores or even CPU. I hope nobody does a CPU training. So again, the limited availability is because tensor cores are available in maximum number of GPUs though, but you need to have that specific SDK, specific things at place in order to access those tensor cores in that specific GPU as well. You need to know what GPU you need to select, and you need to make sure that the GPUs are available with tensor cores as well. Moving forward a little bit. So if you just try to think all the aspects of tensor cores in terms of training and inference, bottom line it would be forward propagation and backward propagation in terms of training, where the tensor cores optimize these two parts in a very better scale, resulting in faster training and getting the results probably in very, very less time, whatever you're trying to do, whatever kind of training. I'm probably in these days, I think we are seeing about generative AI, large scale language models, or probably even PyTorch allows us to do multimodal training. That means combining your audio, video, then words together and generate all your algorithm together. For this kind of operations, for this kind of operations and algorithms, for multimodal algorithms, we would need tensor cores to be at presence to accelerate the process as much as possible. And at the point of inferencing, then tensor cores are better in terms of multiplication operations. That means matrix multiplication operations in terms of feed forwarding. So inference is a very vital part as well. What tensor cores they do at inference is that probably they generate prediction within microseconds if you compare it with CUDA cores. So for example, if it's in a factory somewhere and there is a robotic hand connected, and this robotic hand uses computer vision to pick up specific objects that are not supposed to be at that specific region of interest, and the velocity of the products, velocity of the things which are coming very high towards the camera and the robotic arm is very high. So to match that velocity, even our algorithms should also process the data real-time video stream and predict it within microseconds. These are also supposed to be done very fast. Just to prove that it has to be done faster. So this is a small table that has been provided, benchmark the difference if you use CUDA, if you use tensor cores versus if you don't use tensor cores. The first row which you see and half precision that you observe here, which stands at 18.7, that means teraflops. Teraflops are basically nothing but one teraflop is nothing but 1 trillion floating point operations per second. So NVIDIA P100, where there are no tensor cores, does half precision predictions or training at 18.7 trillion floating point operations per second, comparatively to the one which has tensor cores, which is nothing but Volta V100, which can do 112 trillion floating point operations per second. I think this would, I mean, as you see, a very distinction between 18.7 and 112 here. This would be very critical if your models are at half precision and then you're trying to train your algorithms or infer in real time. It would certainly reduce the time at training at inference as well. Moving forward, I think from here on, my colleague Aniket will be taking over. Thank you.
Thank you, Akhilesh. So, as of now, you have seen what my colleague Akhilesh have mentioned about Tensor Core is like what exactly is Tensor Core, how we can use Tensor Core, and why we should use Tensor Core as well. So, we have prepared a small training and inference graph where it shows like how the performance is when you train or infer something on a GPU with the Tensor Core versus when you see the performance on a GPU with a lot of Tensor Cores. So let's say in the graph here, so we are using a P100 GPU where there's no Tensor Cores, and we are using a V100 GPU. So we have trained and inferred three different YOLO versions, that is YOLO V4, V5, V6, and V7. So here you can see in the P100 side, if you look at the green graph, which is a YOLO V6 model, and on the right side as well, if you see there is the same green graph with YOLO V6 model, both the side, the MAP that is almost same, that is almost around something 53, 54%, sorry, 53, 54. Now, but if you look at the FPS, which is at the bottom, if you look at the FPS for YOLO V6, the FPS on P100 is almost around 40, 41 FPS. And when we ran the same thing on V100, the FPS is 80, which is almost double. So just to be clear here, the model trained on P100 and the model trained on V100 are exactly the same. So the hyperparameters are exactly the same. The image input is 640 plus 640 for both the side. And you see the improvement in speed. Although the accuracy remains almost same, the speed has increased drastically. If you see the another example, if you look at the red graph, that is YOLO V7 graph, there you see in both the side, the MAP is around 55. However, the speed of processing that has increased from 40 all the way to 120. That is almost 3 times there is increase in the speed. So this shows that when we use tensor cores, our speed will drastically increase. However, there are certain ways we can also keep our accuracy constant. We don't, I mean, usually when we use half precision, the accuracy or the gradient tends to fall down, but there are few things which we can use in order to keep them constant. So let's see, currently we know, okay, well, what are the different ways we want to know, what are the different ways we can use tensor cores, what are different frameworks that actually supports tensor cores. So basically, all the deep learning frameworks that are available currently, almost all of them supports tensor core. So example, TensorFlow, PyTorch, MXNet, ONX, and few others are there. So let us see now how we can use tensor code in more of a programmatical way. So in our coding, how do we use tensor code for few of the models? As the time permits, we cannot go with all the models, but let's try to do for one or two of them, right? So let's see how we can use tensor core on a TensorFlow framework, right? So there are basically two ways where we can use tensor core. So the first way is pretty simple and straightforward. All you have to do is just set up the environment variable by exporting the parameter called TF enable auto mix precision is equal to 1. So this will basically set your TensorFlow environment such a way that whenever you do a training, by default, it will start using your tensor cores for using mixed precision. The second way is more into advanced development method where you get to optimize or you get to hyperparameter tune parameters a little bit more. You get a little bit extra option to choose what kind of data type you want to go ahead and train with. That is by creating a wrapper around your optimizer. So as you know, in the mixed precision, we can have both floating FP32 as well as FP16 data type to train and to improve our accuracy or the performance. So this can be achieved in TensorFlow by using by rewriting the graph. So we have the session graph in TensorFlow that we can rewrite in order to change the model weights to FP16 from FP32 in order to achieve our goal, that is achieve a good throughput. But the problem here is if we use FP16 throughout FP16 throughout the model, like the entire model is converted to FP16, the problem will be there is a chance that the gradient can overflow or underflow, which will result in decrease of the accuracy. So the best possible way, what we can do is we don't convert everything to FP16, but however, we use mixed precision where we convert few of them to FP16, and few to FP32. So basically, what we can convert to FP16 is since Tensor Core supports FP16 in a better way to speed up the throughput. What we can do is we can take all the arithmetic operations involved in the model, all the convolutions and arithmetic operation can be taken and then converted to FP16. The batch normalization part where we normalize can be set as FP32. So what that does is actually it will convert the entire model to FP16, keeping your batch size batch normalization as FP32, and this will increase the throughput and also keep the accuracy intact. It will not sacrifice the accuracy at any point. So so this is how you can run this Tensor Core on TensorFlow framework. Now let's see how we can do the same on PyTorch as well. So on PyTorch also we have a wrapper called automatic mixed precision, which is basically a wrapper that will convert the model to FP16 as the same that we did in the TensorFlow. So here also we have we can do this by adding a single line of code in your optimization part. So this particular line of code which you are looking at, the wrap the optimizer will create create a wrapper around your optimizer that will improve your that will leverage the use of Tensor Cores. If you want to use auto scaling, auto loss scaling as well as back propagation scale, so the below line will help you do that. So now let us understand this with an example, how we can use this and how we can utilize this and do our coding. So let's say you see line number 5 here, right? So model optimizer. So basically, this particular line is responsible for converting your model to FP16. Now you see the last parameter here, OPT level, operational level is equal to 0 2. So basically, there are 3 different operational levels that you can set. That is 0 0, 0 1, and 0 2. So what 0 0 actually does is it will convert all your model to FP32 instead of FP16. If you want to train your the model with FP32 data type, you can just use 0 0. If you want to use mixed precision, that is, if you want to use some part of FP16 and most part with FP32, you can set it to 0 1. However, when we are talking about utilizing Tensor Core at its fullest extent, we use 0 2, which means almost everything is converted to FP16, but few are kept as FP32. So basically, what we can do, what we do here is when we convert, as I mentioned earlier, when we convert everything to FP16, it will create in loss of accuracy. However, by keeping uh, most of the arithmetic part in FP16 and then taking the normalization part into FP32 will result in maintaining the accuracy with higher throughput, right? So now let's see how. So we have created some benchmark. We have done some benchmarking on different kind of algorithms, algorithms with different models to see what kind of speed up we get whenever we do any kind of training or inferencing. So for example, if you see on the left side, we have image classification. We'll take an example. So when we do image classification, let's suppose we take a RASNet 50 and assume to train a RASNet 50 model for like 100 epochs, it takes 1 hour. Now, after using Tensor Cores, the same model took almost around 20 to 25 minutes, which is like almost it increased the speed by three to four times. The same goes with the detection model as well, where we see the speed increase in the training as well as inferencing with at least 2.5 times. We did train some translation models, speech and language models as well on different models, where we see the minimum growth or the minimum speed increased was around 1.9 to 2%, 2x, and maximum, I mean, for few of the model, it reached up to 5x also, which shows at the end key whatever model we want to train using tensor cores, we can speed up the things by a lot, reducing the time of training, and we get the best result out of it. So for example, as Akhilesh earlier mentioned, right, we have a class with full of students. Let's say all the students are CUDA, and we have two of the students are let's say tensor cores. So now the tensor cores are specialized on arithmetic operations. Whenever they give an exam, the students are given an exam. So what happens is the two students who are expert in arithmetic operations or in their role compared to all the other students, they tends to finish things way faster compared to the one who are not very expert, who are normal in their role. So this concludes that tensor cores can be used to efficiently increase the boost the training as well as inference time, save our time to do much more experiments in a faster way rather than going with only CUDA cores. So that's conclude thing, and I think if there is any questions, we can take the questions now. Over to you, Aditya.
Thank you, sir. Yes, if you have any questions, you can drop them in the Q&A section below, and sirs will try to answer.
Okay, if you're using. Take the first one, take the second one.
Yeah. Okay. So we have a question. If you are using TensorFlow and PyTorch framework, we can leverage automatic mixed precision features available in those frameworks to activate tensor cores. Depending on our scenario, activating tensor cores can be as simple as adding just 2 lines of code. What is your opinion? Yes, that's true. So to enable tensor core, you just have to add the 2 lines which I had shown in the earlier slides. That will take care of enabling tensor cores for your model.
Yeah, we have another question. Tensor Cores leverage fused multiply addition algorithms. They multiply and add two FP16 and or FP32 metrics, thereby significantly speeding up calculations with less or no loss in the ultimate efficacy of the model. Well, I mean, yeah, exactly. That's true. Not significantly, but you might find in very decimal points. I mean, let's say that your accuracy is at 95 with normal cores, and it might be around 94 point some odd. I mean, if that was your question in terms of accuracy, well, it might be slightly significant, but negligible loss in terms of your efficacy of your model. Probably, I would say predictions. And can TensorGo's magnitude a higher performance with reduced precision like 8-bit floating point in the transformer engine, TensorFlow 32 and FP16. Let me type that. Uh, I didn't understand this. Basically, can TensorGo's magnitude be
Meanwhile, we have this question: deep learning, training, and inference activities are accelerated much more by extra precision format. For instance, can it guarantee up to 20x speed without altering the code? I believe 20x speed it won't. It might not, right? Up to maybe 5 or 10x, you will get the speed without much of the altering. But yes, it also depends on your the GPU or the tensor which you are using. I'm sorry, I just saw a question how to optimize any machine or deep learning task using TensorGo. So TensorGo is not a framework; it's a company that uh, that works on computer vision applications, but it's not a framework or anything that will optimize the task.
yeah. Hey, we have a question from Hitesh. How to determine the IOPS for GraphTep protocol buffer? Maybe I need to check with that, and maybe we can get back to you, or you can email me. I think the contact details are present in the presentation below. Maybe I can just type in my email address.
All right, so I think we are done with the questions.
And
Yes, sir.
privately.
Thank you, sir. It was a very insightful session. And thanks to everyone for attending this session. I thank Srini sir, Akhilesh sir, and Aniket sir for their time and for sharing their thoughts and knowledge. I hope everyone had an excellent time and is leaving with valuable insight. I would just like to let everyone know that NVIDIA A100 is available on E2E Cloud and you can contact us for a free trial. E2E Networks will be having a webinar on deep learning techniques for improving generative AI and voice communication on the 6th of April. Invites will be sent to everyone and we hope to see you there. Thank you, sirs, and thanks for joining and have a nice day.
Yeah,
Thank
thank
you.
you.
Thank you very much, Aditya. Thanks,
Have a nice day.
everybody.
Bye bye.
Bye bye.